Okay, hi everybody. We're going to continue on today with Ohm's law. And Ohm's law we'll be using in every circuit from now to the end of the unit, and you're going to get very comfortable with it. It shows us the relationship between voltage, current, and resistance, and we'll see how that relationship changes based upon the types of circuits we're going to have. But very simply, if you look at the variables we have here, we could define them all, and we've seen these in the past. R stands for resistance, and resistance is measured in ohms. And this tells us how much opposition in the circuit we have to current flow. So resistance goes up, usually current goes down. And we could look in our picture or schematic over here. A resistor is that zigzag line I showed you previously on another page. So that's how we represent a resistor in a circuit. V is our source of potential or voltage that gives the energy to the circuit, where we can have the charges being pushed around the circuit. So that's measured in volts, or just a capital V. The voltage comes from our battery source, and I showed you that symbol before. That's those alternating long and short lines, and the long side is the positive, the short side is the negative. Current is capital I, measured in ampere. We could abbreviate that amps or just capital A. And we don't really show current as a symbol in our circuit, but we know the current's going to come out of the negative side of our battery and into the positive side of our battery, because we follow electron flow in Regents Physics. And I just want to point out two things on our picture over here. Over here on the right side is our ammeter. Ammeter measures current for the circuit. And the way this is connected, this is called a series connection, because the wires go directly into the ammeter and come out of the ammeter. It's inside the loop of the overall circuit, where the voltmeter, which measures voltage, is connected in parallel. A parallel connection for a meter, you're going to have separate branches for that meter going across whatever device you're going to measure. So the series connection, the meter's in the big loop. The parallel connection, you actually have those branching wires that go over whatever device you're measuring. It's important that you learn how to connect these devices, because it is something that's questioned in certain multiple choice and part 2 questions. All right, we're going to be using Ohm's law a few times today to calculate either resistance, current, or voltage. And if you have a hard time manipulating equations, this little triangle will probably help you. And the trick to it is cover whatever variable you're solving for. So if we are solving for, let's say, voltage, I would cover up voltage, right? Maybe I'll make that black so we can't see it. So I'm going to cover up voltage. And in order to get voltage, I'm going to multiply I times R. When they're next to each other, that's a multiplication. So to get voltage, I'm going to do V equals I times R. Okay, let's look at another thing if we wanted to calculate another variable. So I'm going to black out I. Okay, so I'm covering I. If I want to solve for I, now V is over R. So whenever it's V over R, that's a division. Okay, so to get I, we're going to do V over R. And just third one we'll do to show you that it works every time. If I wanted to solve for R, okay, you would have V over I, and that's how the equation is shown on your reference table and also in the packet. So you could use Ohm's law to solve for any of those three, and you just cover up the one that you want. And then if they're on top of each other, that is division. If they're next to each other, that's multiplication. All right, so let's give this a try. Have your calculators ready. And I'm going to pause the video after I show you an example, and then we'll go over a couple more. So example 3 says, what is the resistance? So we're looking at R of an electric frying pan that draws 12 amperes of current from a 120 volt source. So we're looking for resistance, which is going to be V over I. Okay, so that's going to be the 120 volt source divided by 12 amperes. Okay, so you're going to get 10 ohms of resistance. Okay, simple enough. It's really, it's either multiplication or division with these numbers. Gets a little more complicated when we have full circuits, like parallel and series circuits, to look over. So we're just going to get comfortable with the basics today. All right, so pause the video here and try example 4 on your own. I'll go over it in a few seconds. Okay, so example 4, it says how much current flows through a lamp whose resistance is 100 ohms. So that's R when it's connected to a 50 volt source. What is the number of electrons, is part B, that pass through the lamp in 3 minutes? So we have a part A and a part B to this question. We'll start with part A, where we're looking at current. Current, if you look at the Ohm's law equation, is going to be V over R. And if you want to, you can draw that triangle again. V equals IR, and you cover up I. So you're going to cover up I, V over R, and you get that equation. Okay, so we have the voltage, 50 volts, divided by 100 ohms, and you get 0.5 amperes. Okay, now in part B, it says what is the number of electrons? Number of electrons is asking about the number of elementary charges. In order to get that, we have to look at Q, the charges that are flowing through the circuit. So you have to think back to way in the beginning of the unit, where we did our initial equation for current. Current equals change in Q over time. So they gave us the time here of 3 minutes. We never use minutes, so we know we're going to have to convert that into seconds. So 3 minutes is 180 seconds. Then we're going to rearrange our equation. I'm going to bring T up next to I, so it's going to be I times T. And we have the current from part A is 0.5 amperes, and we have 180 seconds for our time period. So the charges that flow are going to be 90 coulombs of charge. But coulombs doesn't give us our answer in electrons. I need to convert from coulombs into elementary charges. Okay, do you remember that conversion? 1 elementary charge equals 1.6 times 10 to the negative 19th coulombs. So the coulombs on the top cancel with coulombs on the bottom. So I'm going to do that now on my calculator. And it should be a large number because we're talking about the number of electrons. So I got 5.625 times 10, and we should have a positive exponent here because we have a lot of electrons, 10 to the 20th E. So that's the number of electrons that pass through this point in 3 minutes. Okay, so that is a brief introduction of Ohm's law. I've also embedded into your lesson for today this PhET simulation, and you can see how I can, if I vary the voltage or the resistance, what is going to happen to current, and that's going to be depicted down here in this drawing. So let's say I go from 4.5 and I double the voltage. Okay, I double the voltage. Let's take my resistance. I'm going to go way down. All right. Whoa. So I could change the voltage, I can change the resistance, and you could see how that's going to affect the current. So let's take the voltage way down. You can see that voltage and current are directly proportional. Whatever voltage is doing, current is going to do. Okay? All right. And now let's see, if I increase resistance, what happens to current? Yeah, so that's impeding the flow of current. So if R goes way up and we keep V constant, I is going to go down. Okay, so you can play around with this and see what happens. And the other thing we're going to cover today is electrical power. Okay, so with electrical power, when going through a battery, work is done on the electron, okay, making it go from the positive side of the battery to the negative side of the battery. This work is converted into energy, okay? And as the electrons move around the circuit, they lose the same amount of energy that they gained. Energy is lost going through resistors or electrical devices. Unless otherwise stated, you could assume that the wires have no resistance, so no energy is lost by electrons traveling through the wire. So basically, what we have to know is that a certain amount of work is done and converted into energy whenever we go through a device in our circuit. And this could be something like a light bulb or a resistor, or if you're powering a radio or some other device. And we can easily find the power by looking at work over time. Okay, we've encountered work before, but it was mechanical work. Okay, but this is the same equation that we used back then when we did work, power, and energy. Power, which we measure in watts. Okay, watts. We could abbreviate it W, but also realize that that is equivalent to a joule per second. Okay, that is our unit for power. W is going to be work, and we can measure work in joules. Okay, we could abbreviate that J. And don't forget, not that we have to use that, this often, but work is force times distance, back from work, power, and energy. All right, and then we're talking about electrical work, electrical power. So we have to incorporate current, measured in amps, voltage, measured in volts, and resistance. Okay. So we also have to go over the additional formulas for power and energy. So if you look, yes, we have the power equation, work over time, but then we have this substitution into the formula, and I can kind of show you where this came from. If you recall from electrostatics, potential difference is work over Q. Okay, and if I rearrange for work, that's going to be V times Q. So if I substitute into that original power equation, P equals, instead of writing W, I could write V times Q. That's still going to be over time. And then you look at Q over T, that's the equation for current that we originally learned. So V times I, which is this formula up here. And then you could substitute in Ohm's law, V equals IR, or I equals V over R, and get the other two formulas. So if I substitute in for V, that would give me IR times I, which is I squared R. If we do the same thing, but this time for I would have P equals V over R times V. So that would be V squared over R. So that's where all of these formulas come from. And they are all on the Regents reference table, if you take a look. And so on the next page, we actually have all different equations for electrical energy. Now you have to keep in mind, we learned back in the work, power, and energy unit that work is energy, energy is work. So if they ask you for the amount of electrical energy, they're really asking you for W. So look at this equation, power's work over time. If I rearrange for W, it's going to be P times T. So I can take any of these power equations, multiply it by time, and get electrical energy. And that is what we see on the next page. P times T. So any power equation that we have, you multiply it times time, and then we have the electrical energy in the circuit. All right, so let's give a couple of these examples a try. Have your calculators ready. And then I want you to try number 6 on your own, but we'll do 5 together. All right, so number 5, it says, what is the power, so that's P, dissipated in a 10 ohm resistor that is connected to a current of 4 amps flowing through it? So you have to go look at your reference table or the previous page to find the best equation that fits. And the one that'll work best is I squared R, because those are the things that we were given. So we're going to have 4 amps, and that has to be squared, times 10 ohms. Okay, so you multiply that in your calculator, you get 160 watts. Okay, because the unit for power is watts. Okay, so try number 6, pause the video, and I'll go through it in just a minute. So number 6 says a lamp with a 60-watt light bulb is connected to a 120-volt source. Okay, so power is in watts, voltage is 120. It says, what is the resistance of the lamp? So that is part 1 of this question, or part A rather. Part B is how much energy is given off by the lamp in 3 minutes. So they're giving us a time period. They're asking us for energy. And remember, that is W, work. All right, so let's do part A first. All right, we're looking for the resistance. All right, so I want to use a power equation that has V and R in it. That happens to be V squared over R. Since I'm solving for R, I'm going to multiply by both sides, divide by P. So it's going to turn into V squared divided by P. Okay, so I'm going to do 120 volts squared divided by the 60-watt bulb. So I get 240 ohms as my resistance. Okay, in part B, they're asking us for the energy. So energy, W, is just going to be the power times the time period. And once again, they gave us minutes. We never use minutes. So we have to convert that into seconds. So 180 seconds is our time period. So we're going to use the original power given, which was 60 watts. We're not using the answer that we found in the previous part of the question, so you have to be careful. So we're going to do 60 times 180, and we get for our energy usage 10,800 joules. And just remember, a watt is equivalent to a joule per second. We're multiplying that by seconds, so seconds cancel, leaving you with joules. All right. Something that I want to mention that is pretty important for this unit is that power is proportional to, that's what that symbol means, proportional to brightness. So if we're talking about light bulbs, the more power there is, the brighter the bulb will be. So that's the difference between buying a 60-watt light bulb at the store versus a 100-watt light bulb. You might want to use 100 watts in a space that you want brighter, like a kitchen, so you could see what you're working on, versus a 60-watt bulb that you might want in a living room or a bedroom that you wanted a little dimmer and a little calmer. Okay, so that's it for today. We're doing just Ohm's law and power and energy today. I'll put up some practice problems for you, and good luck.